This video is on precipitation reactions. By the end of this video, you should be able to write dissociation equations for ionic compounds. You should be able to predict the products of a precipitation reaction. And you should be able to write net ionic equations for precipitation reactions. Recall that dissociation is the term we use to describe the fact that ionic compounds come apart when dissolved in water. For instance, if we put solid KCl, an ionic compound, in water, the K plus and the Cl minus ions will separate or dissociate. Looking at this on the particle level, here we see KCl. The fact that they're touching implies that they are bonded together. And then when they're dissolved, our K plus and our Cl minus ion are no longer touching, so they're no longer attached to each other. Likewise, for silver nitrate, notice in this example, however, we have a polyatomic ion, NO3. So when this dissociates, we get an Ag plus and an NO3 minus. Recall that polyatomic ions remain intact. They do not come apart. And finally, a third example, calcium chloride. Here notice that there's a 2-to-1 ratio between calcium and chloride. Therefore, when it dissociates, we get one Ca2 plus ion and two Cl minus ions. These equations shown here are all dissociation equations, meaning they show the dissociation of the ions. Let's try writing a dissociation together. Let's look at the first example, MgCO3. This is an ionic compound, and it contains a polyatomic ion. We will get Mg2 plus as our first ion, and we'll get CO3 2 minus as our second ion. CO3 2 minus is the carbonate ion, so it does not fall apart further. Pause the video here and write dissociation equations for the other two on this slide. When you come back, I'll reveal the answers. Here's what you should have gotten. Notice in example 2, FeCl3 has a 3-to-1 ratio between chloride and iron. A precipitation reaction is a reaction in which two solutions are combined and an insoluble product forms. This insoluble product is called the precipitate. For example, consider the reaction between the aqueous solutions KCl and AgNO3. These will perform a double replacement reaction in which the two positive ions will switch places, giving us silver chloride and potassium nitrate. Since all nitrates are soluble, we know the potassium nitrate will be aqueous. Silver chloride, therefore, is our precipitate. It's the solid that's formed from two aqueous solutions. Looking at this on the particle level, here we see the two solutions separately, KCl and AgNO3. Notice that in each case our ions are dissociated because they're aqueous solutions. When we combine these two solutions, the silver ions and the chloride ions will bond together and create a solid which will sink to the bottom. The potassium ions and the nitrate ions, however, will remain dissolved in solution. Here's another example of a precipitation reaction. In this case, we're combining aqueous solutions of potassium iodide and lead-2 nitrate. Once combined, a yellow solid forms. This yellow solid is our precipitate, and it's composed of lead iodide, PbI2. The lead and the iodide ions bond together to form a yellow solid. Our K plus ions and our NO3 minus ions, however, remain dissociated and dissolved in solution. Notice also here that we had to consider the charges on each of our ions when creating our products. Since potassium has a positive 1 charge and nitrate has a negative 1 charge, they combine in a 1-to-1 ratio. On the other hand, lead has a 2 plus charge and iodide has a 1 minus charge, giving us a 1-to-2 ratio, or PbI2. When thinking about products of precipitation reactions, it's important to remember our one solubility rule that we've looked at before. Any compound containing sodium, potassium, ammonium, or nitrate ions will always be soluble. For our purposes here, you can generally assume that all other compounds are insoluble, although there's lots of exceptions to that, so you'd usually be given more information. Now let's work on predicting the products for a few precipitation reactions. We'll do number 8 together, then you can pause the video and try the others. Since these are all going to be double replacement reactions, our positive ions will switch places with one another. Be sure to consider the charges when predicting products. We know that sodium has a positive 1 charge, and it's going to combine with nitrate, which has a negative 1 charge, giving us NaNO3. We also know that lead has a positive 2 charge. If you weren't sure, you can tell because lead is combined with 2 nitrates, so it must be positive 2. And sulfate is a negative 2 charge. So these will also combine in a 1-to-1 ratio to give us lead sulfate. Now we have to balance the equation. So I'm going to put a 2 in front of our NaNO3 and our equation will be balanced. And finally, let's consider phases. Since sodium nitrate contains both sodium and nitrate, it absolutely has to be aqueous. Containing either of those alone would have made it aqueous. Therefore, we can assume that lead sulfate is our solid, or our precipitate. Pause the video here and predict the products including phases for number 9 and 10. When you come back, I'll reveal the answers. Welcome back. Here's what you should have gotten. Notice that in the third example, the combination of KNO3 and BaCl2, we actually have no precipitate. Therefore, we would say that no reaction has happened. We haven't created anything new. We just have the same ions all dissolved in solution. We can use a variety of different equations to describe precipitation reactions. We can write formula equations, which are what we've been writing up to this point, which shows the full stoichiometry of all the compounds. We can write complete ionic equations in which anything that is a strong electrolyte or dissociates completely is represented as an ion. So taking the example above, we can dissociate or separate all of the ions in the reactants and all of the ions in the products. Notice, however, we have not separated the ions in our solid product. Because it's a solid, those ions do not dissociate. And finally, the most convenient version, and the version we'll use most often, is the net ionic equation. This includes only the ions undergoing a change and does not include the ions from the complete ionic equation that are not part of the precipitate. For instance, looking back at our previous complete ionic equation, if we eliminate the spectator ions, or the ions not involved in forming the solid, like K plus and NO3 we're left with just the net ionic equation, showing the ions that lead to the solid. Let's try writing net ionic equations. We'll do number 8 together, then you can pause the video and try number 9 on your own. The easiest way to write a net ionic equation is to begin with the solid that the equation forms. So we have lead sulfate. Then we can just add as our reactants the ions making up lead sulfate, which are Pb2+, aqueous, and sulfate, SO4, 2-, aqueous. This is balanced as written, so we don't need to do anything further. Notice that we have not included sodium or nitrate because these are both spectator ions. Pause the video here and try number 9 on your own. When you come back, I'll reveal the answers. Welcome back. Here's what you should have gotten. That brings us to the end of this video. Let's review our goals. First, we learned how to write dissociation equations from ionic compounds. Then we predicted products of precipitation reactions using our solubility rule to predict which compound would be the precipitate. And finally, we looked at how to write net ionic equations for precipitation reactions, which eliminate spectator ions.